Welcome everyone to day one of Unit 14. You should have your new packets on your desk. We're going to look at two main scenarios today when you have a diameter that's perpendicular to a chord and also tangents to a circle from the same point that's outside the circle. As we work through today, we're going to show you some rules and we're going to show you why those rules work out, and then we'll see about applying those in a few problems. So first off, just recap from previous units, and this is nothing that you have to write anywhere to start out. So this first picture here on the top, it's a line segment whose endpoints are on the circle. That's a chord. And then our longest chord is one that passes through the center. That's a diameter. So we just need to be comfortable recognizing those two things, a diameter and a chord. Because notice our first thing we're going to look at today is when a diameter is perpendicular to a chord. So again, no place that you have to write that. All right, if we go over to page 1 in our packets now, in a circle, when there's congruent central angles, they have congruent chords. So what I'm going to do for each of these, we have two of the same picture always. Right over on the right side, the rule. So in the right-hand picture, we're going to mark what the rule is. And on the left-hand one, we're going to show you why it works out. So our rule over on the right-hand side, it says we have congruent central angles. So let's put our arcs on those central angles. And it's saying if we have those arcs congruent, the chords should be congruent as well. So let's put a tick mark on each of those. So that's the rule that's true. Well, I don't want to just give you something and you assume that it's true. Let's show you why it is true based on things we've learned this year. And that's what we're going to use the left-hand picture for, is just to justify for you why our rule is true. So let's go ahead. Let's mark those central angles. That's what we are given. Well, what we want to recognize is our center to A, our center to B, our center to C, and our center to D. Those are all radii, so they should be congruent. Well, notice now those two triangles are congruent by side angle side. Once we have triangles congruent, we know we can do congruent triangles implies congruent corresponding parts, which would then allow any other parts of the triangle to be congruent, and that's what eventually gives us our chords congruent. So that's the why. We don't want you to have to go through that thought process every time now that we know why it is what it is. We just want to know, okay, if the central angle is the same, the chord must be the same as well. Next one, if we have congruent central arcs, then the chords are congruent as well. So let's go over to the right-hand picture first. Let's mark up our rule. So let's mark our arcs congruent, because that's what we started with. And they said that should give us congruent chords. So now let's put tick marks on the chords. And I know it's kind of a tight squeeze there in your picture. So if the arcs are congruent, then the chords must be congruent. Well, in the left-hand picture, let's show you why that's true. So let's start out with the congruent arcs. Something we saw last unit is your arc has the same degree value as your central angle. So if the arcs are the same, then the central angles have to be the same. And then based on the rule we just saw here, if the central angles are the same, the chords are the same. So that's where our reasoning is coming from. All right, going down to the bottom, again, we've got two pictures. We're going to have the right-hand one, we'll mark up what the rule is, and then we'll show you why it is in the left-hand one. So the rule is if you have a diameter that is perpendicular to the chord, it bisects the chord, and therefore it also bisects its arcs. So we've got our diameter CD, the chord is AB. So it says it's going to bisect the chord, so we can put our tick marks on the chords, and then therefore the arcs are going to get bisected as well. So the why for the left-hand picture, I'm going to specifically show you why the chords get bisected, because that's the main one that we're going to work with. So often in this picture, we're going to strategically draw in a radius. The radius we're going to draw in is from O to our endpoints there. So there's really an infinite number of radii you could draw, but we'll purposely draw those ones in. Well, we know that all radii are congruent, so we can put a tick mark on those. This would have to be a right angle as well, and by reflexive property, that little segment is congruent. Well, notice now we have angle side-side. Angle side-side we saw does not work in general, but if your angle is a right angle, then our two triangles are congruent by hypotenuse leg. Once the triangles are congruent, congruent triangles implies congruent corresponding parts, allows us to get any additional things in the triangles congruent, and that's why we know each of the parts of the chord have to be congruent. Now again, you're not going to want to have to do that justification on every problem, so one of our big rules for today is what we have marked up here. If you've got a diameter perpendicular to a chord, we want to be able to jump to those purple marks there that the chord gets bisected, so each of those parts are congruent. All right, one more thing with chords and diameters over on page 2. So first off, let's talk about what's meant by being the distance from something. Now, I am not in the room right now, but let's imagine I was standing somewhere in front of the smartboard, and I wanted to find my distance to the back wall, and I was going to measure it with a tape measure. When I measure that with a tape measure, I would want to make sure the tape measure forms a right angle with the wall. Because when you measure distance to something, you measure perpendicular distance. I wouldn't want to measure from in front of the smartboard to by the flag. That wouldn't be my actual distance to the wall. The distance should be a perpendicular distance. So when we say the distance that a chord is from the center of the circle is the length of the perpendicular segment, that's why we're saying we've got to measure at a right angle. So in these pictures, the right angle is there to represent that it's the actual distance from the center. So our rule, again, we'll make the right-hand one be the rule. If two chords are the same distance from the center, that's what's meant by equidistant. They are equal distant from the center. Notice we've got that marked up with the tick marks. Then those chords are congruent. So I'm going to show those with a bracket. So then that distance is congruent to that distance. Now to show why that is, we're going to strategically draw in a radius. We'll draw in our radius from center to A, or sorry, center to B and center to D. Radii have to be congruent. Well, now again, we have angle side-side, but the angle's a right angle. So the triangles are congruent by HL congruent to HL. By congruent triangles implies congruent corresponding parts. We know those are the same. And because we have a perpendicular coming from the center, we know from the previous page that the chord gets bisected. So that's why the chords must end up being equal length. So let's see now, we're going to see 6 different examples where these rules get applied. So down on the bottom of page 2, we got circle A. We learned last unit that that means A is our center. And we've got AF is equal to AG. So let's mark those up with tick marks. They tell us BC is 22. So let's label that with a bracket. And we want to find what DE is. So we can call that a variable. Well, what this is showing is that each of our chords are the same distance from the center because it's that perpendicular distance. We saw that if up on the top of this page, if you're equidistant from the center, that the chord should be the same length. So this should just also be 22. So DE is 22. Now it doesn't ask for it, but we could find the length of BF, FC, DG, and GE as well, because if the chord is connected to the center with a perpendicular line, then that should get bisected. So each of those smaller ones, BF, FC, and so on, are all actually 11. But it didn't ask for that specifically in this problem. All right, if we go over to the next page, in all 4 or in both these problems on top, A and B, circle P, so that means P is the center. We have a radius of 10, and A, B, and D, E are perpendicular. So because A, B, and D, E are perpendicular, I'm going to draw in my right angle there. They told us that the whole thing, AB, is 8. Well, we saw in some of the previous slides that if a chord is perpendicular to any line going through the center, be a diameter or a radius, the chord gets bisected. So we know that both of these should be 4, so therefore AC is just 4. Going to part B, again, we know the radius is 10, and we had AB and DE were perpendicular. So we know that this is going to get bisected, so those two are equal. They tell us that DC is 2. And they tell us that the radius is 10. We eventually want to find what AB is. So a couple things we're going to do. We're going to strategically draw in a radius, either from P to B or P to A. It doesn't matter. We know that radius is 10 because it was told to us in the problem. Now remember, all radii are congruent. So we know P to B should be 10, P to A should be 10, P to E should be 10, and also P to D should be 10 as well. So this length from P to D should also be 10. Well, if D to C is 2, that leaves us 8 here for P to C. Well, now let's just pick a variable that's not in the problem, and we've got a right triangle. So we can do Pythagorean theorem. We can do x squared plus 8 squared equals 10 squared. That'll give us x squared plus 64 equals 100. We'll subtract the 64 over. We'll get x squared equals 36. And if we take the square root of both sides, we get x equals 6. Now there's a common right triangle that you see that's called a 3, 4, 5 right triangle. 5 would have to be the hypotenuse because it's the longest side. And you could see that 3, 4, 5 triangle with sides doubled, tripled, quadrupled. This is just a 3, 4, 5 triangle with all the sides doubled. Well, we just found that x was 6, which was CB in our picture. We want to find AB. Well, because the chord is perpendicular to the diameter, we know AC has to also be 6. So therefore, AB is just 12. It is very common when you see the chord perpendicular to the diameter that you want to draw in that strategic radius to turn it into a right triangle. That happens in a lot of problems. All right, if we go down to 3, notice we've got the tick marks and we've got circle G. So that means those chords are going to be the same distance from the center. So automatically we already know that AC and FD should be congruent. So we know here to here is equal to there to there. Because if you are the same distance from the center, those chords should be equal. Well, they tell us that EF is 12. We know the chord gets bisected when it's perpendicular to any line going through the center. So this is 12, meaning the whole thing is 24, meaning that AC also has to be 24. And the next one we got circle B, so B is the center. AB is 10, so we should be able to automatically label BC as 10. We also know that B to E has to be 10, because they are all radii. They tell us AC is 16. Because the chord is perpendicular, meaning forming a right angle, with any line coming from the center, this case a radius, it's going to get bisected. So instead of labeling 16, let's label 8 and 8. Well, we have a right triangle, and 8 and 10 are 2 of the sides. Let's reuse what we saw above. We saw a right triangle, a 3, 4, 5 with everything doubled with 6, 8, 10. Well, we've already got the 8 and the 10, so that means our other side just has to be 6. Eventually, we want to find DE. Well, notice here we have B to E is 10. If B to D is 6, then that leaves us with just 4 for DE. All right, one more thing with these rules, then we'll see a rule with tangents. So in number 5, this is over on page 4, we've got circle O, so that means O is our center. AB is 30, so we'll label that with a bracket. OM is 20. ON is 18. And we want to eventually know what CN is. So I'm going to call that X. Well, if AB is 30, because OM is perpendicular to AB, we know each part is 15. And what we can do is we can strategically draw on a radius. Let's call that Y. And let's do Pythagorean theorem to find Y. So we're going to have 15 squared plus 20 squared equals Y squared. This will give us 225 plus 400 equals Y squared. Or 625 equals Y squared. Take the square root of both sides, and Y is just 25. So this length is 25. And how that's helpful is we can draw on a radius from O to C, and we know that has to be 25 as well. Well, now we have another Pythagorean theorem we can do. We can do x squared plus 18 squared equals 25 squared. Now before we go on, I want you to look at that triangle, the 15, 20, 25. That's also a 3, 4, 5 triangle, but everything's just multiplied by 5. 3 times 5 gives you 15, 4 times 5 gives you 20, 5 times 5 gives you 25. So if we do our Pythagorean theorem to find x now, we'll have x squared plus 324 equals 625. Subtract the 324 over. X squared will equal 301. And if we take the square root of both sides, x is just equal to square root of 301. That doesn't menu number factor at all, so that's just our final answer. So Cn is just the square root of 301. All right, moving down to 6. First off, a refresher, a tangent line. A tangent line is any line that hits the circle in exactly one point. If it hit in 2 points, we would call that a secant line. So if you have a radius that meets a tangent at a point on the circle, it'll be perpendicular. So let's make this one be our rule. So the rule is it's going to form a right angle. And let's show you why that is. If we extend this radius to be a diameter, we know that these are each 180. And then because that angle's on the circle, it should be half of the arc, so this would be 90 degrees. So a radius that meets a tangent line at a point will always form a right angle. It's got to be perpendicular. And then our last rule that we'll look at today, this is over on page 5. If two segments start from a point outside the circle, and they are tangent to the circle, then the segments are congruent. So over on the right here, we'll mark up our rule. So notice we have two tangent lines. What that's saying is B to A and B to C should be congruent. And we're going to show you why over on the left here. So again, we're going to want you to just memorize this rule, but I don't want you to just think we're pulling it out of thin air, so we're going to throw you why, or show you why. So let's connect O to B, connect O to A, and O to C. Well, O to A and AB should form a right angle, because that's a radius and a tangent meeting. Same thing at C, we should have a right angle. We have radii that are congruent, and then we have a reflexive property. So we have angle side side again, but the angle's a right angle, so those two triangles are congruent by HL. And then by congruent triangles implies congruent corresponding parts. That gives us these segments congruent. So that's the why behind it. We're going to want you to just be able to jump to knowing that if you have tangents from the same point outside the circle, they should end up being congruent. Now down on the bottom, how many tangents could a circle have if you have two circles? Well, as long as the circles aren't the same size, you should be able to come up with 4 tangent lines. And let's see if I can do that here. And you can just kind of freehand draw them in on your paper. So we should be able to come up with, there's one of them. There's a tangent line from a bottom where it's just hitting both of them. We should be able to come up with one like it on the top, where it just barely hits both circles. So there's a tangent line on the top. And then we should be able to do some with a crisscross as well. So let's see, I'll have to adjust them a bit. All right, so there's roughly that one. It's hitting each circle in only one spot. And then we could do one going the other way as well. And again, I've got to adjust it because I'm just freehanding these in. We've got to adjust them so they just hit the circles at one point. So there's 4 that we could do. Now, you probably won't have to see that. There was once a long time ago a multiple choice question on the Regents to ask this. That's why I throw it in the notes. But you probably won't have to work with that. So our last page for today, page 6, we're going to use our idea that if you have tangents from the same point, they should be equal. So in this one, we've got 2 expressions. These are tangents from the same point. Tangents because they're only hitting the circle in one spot. So they should be equal. So 3x plus 7 should equal 7x minus 9. We'll solve for x. I'm going to subtract 3x on both sides. So 7 is going to equal 4x minus 9. We'll add the 9 over. We'll get 16 equals 4x. And we'll divide both sides by 4, so we'll get 4 for x. In this course, always reread the question, see if that's what we wanted to find. And in this case, we just wanted to find what x is, so we're done. All right, our last problem for this video, I think these are kind of fun problems. It looks like a circle inscribed in a triangle, but instead I want you to think of it as 3 sets of tangents from the same point. You have A to F and A to B. Those should be equal. E to F and E to D. Those should be equal. And then C to D and C to B, those should be equal as well. And that's because they're tangents from the same point. Well, they tell us that AE, this whole thing is 15, and EC, this whole thing is 19. And then notice we already had this 6. Eventually, we want to find AC, so I'm going to call that a variable. Well, because AB is 6, AF must also be 6. Well, then they told us AE was 15. If that whole thing is 15 and we have the 6, then EF must be 9. If EF is 9, ED has to be 9. And then if that whole bottom is 19 and ED is 9, then we've got that DC has to be 10. Therefore making BC be 10. And AC altogether then would just be 16. So they're kind of like dominoes start falling. They'll give you enough information that will eventually allow you to find whatever you want. All right, any time left in the period, you can be working on your day 1 homework that is in your packet. Have a great rest of your day.